Hi everyone, I'm Nikhil and today I'll be presenting our work called Informed Steiner Trees, an approach for multi-goal pathfinding in high dimensions. This work would not have been possible without my amazing collaborators, Kenny Chul and Professor Sivakumar Rathanam from Texas A&MU and Professor R. Ravi from Carnegie Mellon. The motivation of our task is to consider a robotic arm whose end effector must reach several goal placements with a fixed origin and destination. This arises in several applications like spot welding, car painting. For example, here the robotic arm is painting red and it may have to paint red somewhere else as well. Or in tasks like surface inspection, active perception, and more. The objective is to compute a near optimal path visiting each goal once. An optimal path would be the one which has the least cost, and the cost is generally taken to be the length of the path. The problem is formally known as the multi-goal pathfinding problem, and it has two variants. In the discrete case, the search space is finite and known a priori, and the problem essentially reduces to the Steiner traveling season problem, which is NP hard. In the other case, the search space may be continuous and we may have no clue about the least cost path between any two goal nodes. An example of this is shown on the right, where we are essentially given the location of 5 goal nodes and a representation of the obstacle region. Here we see that the obstacles are arbitrarily shaped. However, even if they were polygonal, finding the shortest path in 3D spaces is also NP hard. To address these challenges, we appeal to the well-known sampling-based methods. Their general schema is as follows. We generate collision-free samples directly from the configuration space of the robot and connect nearby ones using a local planner. These are used extensively in practice for motion planning, and they do not require any prior information about the obstacle region. They only assume the availability of a collision checker and in principle can work in any dimension. Going back to the schema, and to our original problem, suppose here we sample the whole space randomly and we end up with this samples and we connect the nearby ones and get this graph. For the discrete version of our problem, this graph would be the input, and using search techniques we can find the optimal path. However, a drawback of randomly sampling from the whole space is that we may end up generating samples which are not useful in pathfinding. To overcome this limitation, Gamble et al. Proposed informed sampling, and it works as follows. Consider the problem here where on the left, RRT star is used, whereas on the right, RRT star with informed sampling is used. The green node is the source, and the red node is the destination, and the black boxes are the obstacles. And what we see is that on the right, samples are only drawn from this ellipse, and any sample outside this ellipse does not improve the length of the path. Here, the ellipse is bounded by the length of the path as its diameter, and the focal points being the source and the destination. Whereas in RT star, samples are drawn from all over the space, and thus it requires significantly more iterations to converge to the same solution. So our approach is on how to extend informed sampling from two goal nodes to multiple goal nodes. And our framework provides a two approximation to the multi-goal pathfinding problem in continuous spaces and uses informed sampling in synergy with a pruning heuristic to significantly accelerate the convergence rate of our solution. IST star essentially maintains 4 different graphs. First is the roadmap graph, as we saw, which contains the goal nodes, the sample points, and the edges between them. Second is a subgraph of the roadmap, which is the nearest terminal graph. We use the words terminal and goals interchangeably. This graph is essentially a forest where each goal node is a root of a tree, and we maintain shortest path from the goal to the sample point within its component. Third, we have the terminal distance graph, which only contains of where the only nodes are the goals, and each edge between any two goal node, for example, this edge is a path in the roadmap graph. Finally, we have the Steiner tree, which is a subgraph of the terminal distance graph. And basically, the mineral spanning tree of GT is essentially the Steiner tree in the original graph. One question that one might ask is, should we maintain cost of all the edges? If we can rid of some of the edges, then we won't have to sample around their region, and thus we can converge quickly. First, we introduce some notation. Let LBE be the lower bound on the optimal cost of HE. This is generally taken as the straight line or Euclidean distance. Let UBE be the upper bound on the optimal cost. This is the current estimated cost of that edge. Let EST be the edge set of the Steiner tree. So here the black curved lines are the edge set of the Steiner tree. And let CE be the cycle formed by adding an edge E to the Steiner tree. So here, if E is this edge, then this is the cycle that is formed. Now we recall a famous and well-known cycle property of spanning trees, which says that for any edge E not in the Steiner tree, let E star be the edge with maximum cost in the cycle enclosed by adding it to the Steiner tree. So here E star is this edge. The cycle property states that if the current cost of E star is higher than the current cost of E, then essentially we can replace E star with E. So E can kick out E star and come at its place as it reduces the cost of the Steiner tree. So essentially E star is the opponent of E in some sense. And the motive of E is to reduce its cost to become lower than that of E star. Based on this, we can come up with a Pruning heuristic that states that for any edge E not in the Steiner tree, if its lower bound is strictly greater than the upper bound of its opponent, then it can never be part of the Steiner tree. This is because of the fact that E can only replace E star if its upper bound is less than the upper bound of E star, and the upper bound of edge E is always greater than equal to its lower bound, and if that is strictly greater than E star's upper bound, then essentially E can never replace E star, so it can never be part of the Steiner tree. Now, moving forward to informed sampling, we saw that current informed samplers are best suited for 2 terminals only. And can we hope to extend them for multiple goals, say maintain LSFs like in this format? To achieve this, we assign a probability distribution over all the edges of the graph GT. For consider an edge E, if it is already pruned, then we assign probability of 0 for it to be sampled, as it can never be part of the industry. Second, consider edge E which is not pruned. So our general intuition is that we should sample more around the regions of edges which have higher uncertainty about its cost. This is based on the assumption that the more we learn about the cost of an edge, the better decision we can make regarding its inclusion in the Steiner tree. So if E is already in the Steiner tree, then our uncertainty is basically the difference between its upper bound and lower bound. So we assign a probability in proportion to the difference between the upper bound and the lower bound of the edge E. However, if edge E is not in the Steiner tree, for example, in this case, the Steiner tree has changed, so E is no longer part of the Steiner tree. In that case, the first goal of E is to become a part of the Steiner tree, and it has to kick out its opponent E star. So essentially, its job is to become better than E star in its cost, and then later hope that it achieves its lower bound. So here, if E is not part of the Steiner tree, we assign a probability proportional to the difference between its current cost and the current cost of the edge it would have replaced, i.e. the current cost of its opponent. Finally, we note that only the edges with non-zero probability can potentially improve the cost of the Steiner tree. Now, summarizing this framework, we run a main loop until the maximum number of iterations or timeout is reached. But the first step is to generate new samples on the roadmap graph. So we have this location of the goals, we generate new samples, and finally obtain the roadmap. Second step is to update the nearest terminal graph, which maintains the shortest paths. Third step is to update the terminal distance graph and prune the edges which we have identified that can never be part of the Steiner tree in future. Next step is to update the Steiner tree. Here we have changed the Steiner tree of this to this. And finally, the last step is to update the probability distribution to reflect the changes in the cost of the edges. We next show an illustration of this framework. So here the gray dots are the sample points and the pink circles are the goal nodes, and these are the obstacle regions while they have narrow passages. And next we show the path between every pair of goal nodes. So this is the yellow line is the path between every pair of goal nodes. And finally, we show in blue the minimum spanning tree or the Steiner tree, which has cost 1.2. And in red, these are the ellipses which show the informed set for each edge, whereas in red are the non-Steiner tree edges. And finally, we see that we will only sample points in these regions, and the roadmap is densified around these regions. And we see that the path of the existing path has improved. So earlier, the path had an ellipse of this cost, whereas now the ellipse has shrunk in size because the path length has improved. Similarly is the case for other edges. And moving forward, we see that the cost of the minimum spanning tree has reduced to 1.08 roughly. And similarly, the size of the ellipses have shrunk down. And now this has the highest probability of sampling because the difference between its current cost and its lower bound is highest compared to other edges. Further, we see that this edge can be pruned because its lower bound, which is the Euclidean distance, is higher than the cost of its opponent, which is this probably. It is higher than the cost of all the other edges in the Steiner tree. And even this one has higher cost than all the other edges in the cycle it encloses. Thus, we prune all the edges which were not part of the Steiner tree. And further densifying, we see this as the new samples. And finally, the cost of existing edges has further reduced. And what we see is that the cost of the Steiner tree has gone down to 1.04554. And now the density has increased here while it was largest earlier here, because the deviation is highest for this edge from its lower bound, while this edge has almost approached its lower bound. Thus, we come to the end and we see how this framework works. Going to the next slide of experimental results, we compare approach with prior works, namely SFF star, multi-DRRT, and lazy TSP. We note that all of these approaches have their implementation only for 3D environment. So we can only test them in 3D environments, though in principle they could work in higher dimensions. For the problem input, we consider 3 cases: 10 terminals, 30 terminals, and 50 terminals, which were generated randomly for each environment. And for the baseline, we uniformly sample from the whole space until time off and form the roadmap, and then run SGAR, a recent state-of-the-art framework for discrete multi-goal pathfinding. For environments, we considered 5 3D environments, some of which are from Open Motion Planning Library, and 2 high-dimensional environments. Next, for our first evaluation, we note that lazy TSP could not find a solution in the given time across all the problem instances, so it is not shown in the bar plots. Second, multi-DRT is only able to find a solution in the triangles environment and in none of the other environments. And further, it is much worse than rest of the solvers because it stops after finding the first solution. Third, SFSR performs really well for the case of 10 terminals, reaching almost the lower bound, like it is shown in blue color. However, as we increase the number of terminals, it is not able to find solution in few of the environments, and for 50 terminals, it times out in 4 of the 5 environments, and even here, when it does find a solution, it is worse than baseline and IST star. Further, baseline consistently find good solution forms only marginally worse to IST star, making it a competitive alternative for our next evaluation in higher dimensions. And we see that for R4, the baseline is stuck at a suboptimal solution while IST star is able to converge quickly to the optimal solution. Similarly, in R8, finally concluding our work, we have developed an asymptotic to approximation framework to address multiple pathfinding in high dimensions using informed sampling and pruning. Further, our approach is decoupled in the sense that any further advancements in informed sampling or roadmap capabilities can be used to update the corresponding component in our framework. For future work, we Can we consider removing samples and identify ones which cannot offer any further improvement to our current Steiner tree? Further, can we obtain tighter lower bounds that can lead to faster convergence, as that would definitely improve the convergence rate of a solution? Thank you for your attention. This concludes my talk.